First of all, thank you for making it through, getting to the third day. Today will probably be lighter. We'll have conversation, and we really want you to participate and feel free to ask questions if you have something about the conversation going on or stuff that we mentioned at class and you want to get like further explanation because we did a terrible job or something like this. So let's start. First we have Raminder from AWS. And we have Sam from NVIDIA. And you know Eric from Classic. Would you like to introduce yourself in a couple of sentences?
Yeah, sure. Myself, Parminder Singh. I'm based out of Dallas, Texas, and have been in AWS last 3.5 years. I joined AWS as an architect supporting the autonomous vehicle and software-defined vehicle. And last year, I changed my course to support the quantum computing initiative at AWS. And I am also pursuing my master in quantum computing out of University in Madrid. That was one of the reasons why I did switch, but I have overall like consulting experience with some of the major consulting companies of the world like Deloitte, Capgemini and all.
We will talk about the point of Madrid and you all of a sudden getting your master's, so we'll get to it.
Oh, yeah.
I'm glad that you mentioned.
Oh yeah.
Hi everyone, my name is Sam. I'm based about 3 blocks away from here in Cambridge. And I lead the product team at NVIDIA for quantum computing. So responsible for strategy and roadmaps for what we build. I came from a physics background, worked at a quantum computing startup called Rigetti Computing for about 3 years. Worked on quantum control systems at a company called Keysight for about a year. Now I've been at NVIDIA for 1.5 years. Very happy to be here.
And you all know me already. Feel free to ask questions if you want to know more, but you got that introduction right from Classic, technical marketing manager, and your co-professor for the last 2 days.
All right, so start with you, Marina, if you don't mind.
Yeah, sure.
So at the moment, you mentioned that you moved to the quantum side at AWS, right? You are global tech leader. So do you mind explaining a little bit about your role and your team and how do you fit in AWS in general and maybe inside like the quantum sphere in more particular?
Yes. So there are various business units in AWS, and one of the business unit is the partner org. And I work with our independent software vendor like Classic, Q-Control, Bit Chemistry. And within the quantum computing at AWS, we have like CQC, who are focusing on building the quantum computer out of Pasadena, California. And there is a Bracket team who interface with all the QPUs. So we are the go-to market face of the Bracket team. But mainly my day job looks like talking with Classic, talking with Good Chemistry. So apart from just integrating the software solutions with the Bracket, we talk with our partners like what are the business use cases or the industrial use case they want to apply. Now some of them would be in between HPC and quantum inspired. So what else I can tell you about? And we do work with the research scientists on the algorithm side and all, for start the design. And then the whole idea is like to fund some of this initiative through the proof of concept and giving out the AWS credit so they can quickly do this experimentation on the AWS and then with all the hardware available on the Bracket side, right? But apart from the Bracket service, which is not actually quantum computer is getting built at the Pasadena in California with the Caltech. The Bracket service is complemented with other AWS, 200 plus AWS services, whether it's machine learning, whether it is serverless and all. So when partner come to us, we look at that holistic view. You want to integrate your solution with the Bracket, but then, how are we going to design your core solution So, and the cloud is the perfect place to experiment this, and then that's how it gets started.
And so I think we kind of talked about it, and we touched on the matter that when you want to get into quantum, you need someone to kind of walk you through at the beginning until you get the hang of it. And also, part of the things are finding the right tools for the problems that the customer have, right? Finding
Yeah.
which applications make sense at the moment, what will make sense later on, right? And in your background, you have like heavy background in cloud technologies in general, right?
Yes.
And now you kind of moved into brackets, so you're more focused on the quantum side of it. So can you share a little bit about what is different, what is similar between doing cloud for quantum and the other, like the classical side of AWS?
Yeah. No, that's a big question. I will try to dissect it in parts. The role which I played last 20 years, so before moving there was into the quantum world, was pure consultant coming from the initially starting on the classical computing on the Microsoft.NET and Python, open source and all, and it evolved into the cloud as I progressed. But then when I was progressing, I saw this field, quantum computing, when I went to one of the Microsoft build session in Seattle and their CTO. It was just like, I just entered the room and the CTO was explaining like, how is this quantum different? This is almost like you can simulate nature and all that. So that was like 3-4 years I saw, and then I was curious enough to come back and started a little bit of my own self-study. And then when I was progressing on this, so I made a conscious decision, like this is the field I will. Now, the reason why I want to tell this story to all of you, I work for AWS full-time job, but as I said, like I have my master going on, I have thesis pending, which I have to start, but it is from student to student because most of you guys are still studying. And this field has a role for everyone, including the high schooler, including the research postdocs, people who have graduated in the quantum physics and they want to do. So we need all the firepower. So now, how we at AWS see this is, we want to give avenue to the students, to the research scientists, or the faculty, or the corporations, so that they can experiment their quantum experiment with ease. So that was the whole point of getting the bracket launched like 3 years ago. So we saw like Rigetti, IonQ, all of they had a QPUs in the data center, but then we came up with this idea, our team came up with this idea, like let's integrate them, put it into the cloud as a hub. And we said like this is a hub because this is like a wrapper or a service hub, which you can submit a job through a Jupyter notebook or through the Conda or through the cloud, any of them. And this hub can go into those 4 or 5 QPUs which you want to simulate. But that is not the point. The point is like, we want to give this to the students and researchers with ease. They can experiment with the quantum algorithm or the quantum program they want to do. So I don't know if I answered all of your pieces, but we can come back to, as students want to know more, like how we facilitate those.
And you mentioned your master that you're doing in quantum technologies in general, right?
Yeah.
But you also participated in Qiskit Summer School, and you had some certifications from Xanadu using PennyLane, and we talked about like how you can break into this industry, right? So, from your experience, what would be the first steps that people can take if they want to start understanding it better, or not be an expert by themselves, but just bring this knowledge to the organization and start using quantum?
Yeah, so I think like it is fair to say, when I started my first day with quantum was like, what the heck this is? And some of the foundational mathematics and physics, I had to go back because I graduated, I did my Bachelor of Engineering 20 years ago. Now, I almost forgot what vectors and matrix multiplication. So it's advice from one student to you all. When you are going through some of the basic foundational, you will not get that day one. Stick with that regime, that your studies, come back, then do the revision again. So you will build that foundational. Now, you don't have to know everything about quantum mechanics, like black body radiation and all that. Give a quick read. Give a quick read on how the math function behind this, and then just go ahead with the fundamentals. The notations like bra, cat, and all is very new. It threw me off, and for me, I spent my 22 years in a classical side, right? Like it was very hard for me to unlearn. For you guys are still starting, you're still studying, so some of this will be very easy for you. But pick up some of the summer schools like IBM's one, and we also offer internship on the AWS side. If someone is interested, they can rope into those programs. But I think like if you want to dive deep, a lot of that is relying on you to do a self-study, go through some of the archive paper, go through some of the Nature article, and you need to be curious. And the field is such a new field, you can ask for advisor, but advisors themselves are trying to come up with the novel algorithm and all. As I was saying yesterday, right, the quantum money, somebody asked me like blockchain, why you need blockchain and all. There is a reason for a new way to think about quantum money in the finance side on the quantum side. And then Peter Shor and a group of others published a paper in the month of May, and that got redacted because someone found a flaw. And then, this tells me like nothing is settled yet, okay? On the quantum hardware side, who will be the front runner after 10 years in terms of mass adoption? We don't know that. What we should do is like try to have a breadth of all this technology and then find a area where you want to deep dive. Some of you will become a business leader, right? Because I thought like I heard it was a mixed crowd. So think about like some of the classical solution or algorithm may not be able to do that job what quantum is offering. But at the same time have your pros and cons and trade-off in the near term, like what is applicable. It may be quantum inspired, and some of this negotiation when you will do with the hardware provider or the system integrator, it may start with quantum talk, but it will lead into the HPC or in between, like parallel cluster and then with NVIDIA or other chip providers there. So, but have a open mind. You don't have to know everything day one. As you progress, these things will come naturally to you guys. That is only, I think, big advice I can give from a personal experience from last 2 years while studying the quantum computing as a subject.
Has AWS published any research in quantum computing?
Oh, yeah. I mean, if you ask me, apart from quantum computing, we have all the other services, right?
Yes.
So there is a various business unit. We are in association with the Caltech. We have like 100 plus team member working on building the quantum computer with a superconducting modality, right? That is business unit itself. It's progressing. We don't know when we'll come out, but there is work going on, right? There is a center of quantum networking. They are based out of Cambridge, and all of the team members are, I think most of them are from the local colleges and local regions. But we recently did a joint publication with Harvard on work on the networking side, quantum internet, because that will be the foundational way to communicate between your classical or quantum computer. So you need that. So the effort is going on. So there is if you go to the AWS and search AWS blogs, so you will find a home page and then you can dissect like quantum computing, and then you will see all the major blogs which are the articles published in that blog, including I believe from our team and also like in conjunction with our partners, whether it is QPU providers or whether it is like a partner who built these solutions. So you guys can see that.
And follow-up question, does AWS Braket supports many quantum computers?
There are 5 at the moment.
Okay.
The Trapdyne, the Anq, and then Rigetti, and last year there was this Lucy from the Oxford side of Oxford Computing. And we recently launched the cold atom, which is like a neutral atom from the Cura. And Xanadu the photon. So we have like a three types, kind of 4 types, and then 5. And all are available under like brackets. And if you are experimenting in your Jupyter notebook, then it is easy for you to switch to one versus the other, because you switch the circuit and there is a standard way, like there is adapter, the bracket adapter, which you guys can use to submit your job task and get the result back. But there are 5 at the moment, and there are 3 simulators, SP1, TN1, and then the density matrix one.
Yeah, that was part of what we showed yesterday when we went to AWS Bracket. We showed some of the circuit connectivity of those computers, as well as the cost to run them. That was on there.
Yeah.
Quick question. You said you don't really need much knowledge about the quantum computing in order to get into the, but is there, to get into the field, but is there a baseline though? Because MBA student here, so.
I missed that last part. You said, is
Is
there?
there a baseline? Is there like,
Minimum requirement.
yes, minimum?
So I don't think so. There is a minimum requirement, because if you see all the summer schools which Xanadu or even the IBM and in some of the cases AWS is working, there are high schooler. So high schooler, they are very fresh in terms of like their maths and the physics background, and they may not know everything about the quantum mechanics, but you don't need to know quantum mechanics, because the role is like if you want to build a quantum computer versus you want to program or software on top of quantum computer, or you want to focus on quantum internet. It depends upon which area you will finally go into. But you don't need to have like A grade in all of this like your physics or the math. There are a lot of material to solidify your base. If I think like I probably when I started 3 years ago, I just revised myself on the vectors, multiplications, and some of the way the matrix multiply and all on the math side. But I completely skipped whole of the quantum mechanics. And part of that reason was like I was doing the quantum computing, which was more about the programming aspect of. But if some of you will go into the field of building a quantum computer, that's what you want to do, then maybe like quantum mechanics and some of the other things on the physics side is maybe important to those students. Because it depends on which area you will focus on the long run. But forming a common baseline, there are enough literature on YouTube's. And if you guys want to go very deep after a baseline, John Friskill's lectures are free. If you go there, John goes into some other topics like cryptography, very deep. And then again, you will not get at the first go. What the heck is this? So you may have to come back in a couple of months, and things will naturally start falling into place. And I see you guys are still getting molded because you guys are doing this graduation either in the engineering side or on the MBA side. This is a perfect opportunity to get into this field. So summer schools will come in month of May, right? May, June, July. I don't know what will be the topic from IBM this year. But apply for those internship or the summer school on AWS side. If you search the internship, quantum is one of the internship you can opt for, but machine learning or anything else, submit an application. I think it's open in a couple of days now. And if you get selected, go and work in that mode like intern, and then while you're working, you will know more.
Thank you. I appreciate that, but I passed the internship with a couple of us here are second year MBAs. So, please, yes, it's for both of you.
Yeah, I think it depends a lot on what you want to do.
Business development.
Yeah, so quantum computing is an industry not that different from another developing disruptive tech industry, and so every kind of job is possible if you're doing like business development is not so different from doing business development on other types of technology, and it's not, there are things you need to learn as you go, but I don't think you need like formal coursework. And actually, if you look at, plenty of CEOs of quantum computing startups are not from a technical quantum computing background. Some are, and you do need people in the company who are, but depending on what you want to do, I don't think there's much requirement for like formal background. I think it's not so hard to pick up and not so different from like other types of very new technology.
Can I ask one more follow-up question, and then I'll leave the floor to everyone else. So, like, Amon, when he was interviewing, mentioned that when you're starting in the field, you need a bit of like hand-holding in order to like understand what is possible, like even within the business development, and then figure out your areas. Do either of your companies offer that in any way?
So hand-holding to me is
Or
internship
like
again.
introduction to
I think perfect or the most optimum way to work in a big firms like NVIDIA or AWS is sometimes this internship is there, right? Like that is one way to do that. But then if you ask me, like, is there someone willing to spend a week with you to explain what quantum fundamentals and what it means for the business candidate in a formal way? I don't think there is a program. I may be wrong. I didn't see one which is done at a level in a graduate or that level. Lot of work is the individual contribution from the post doc and the research scientists and all that. Now, particularly the MBA one, if I have to pick where you guys can contribute, as I was saying yesterday, is this whole CTA Act by design. What it means, like every agencies, and state agencies have to prepare themselves for this quantum business. And even the organizations, public sector, semi-public, private, they have to be ready with this. A graduate in the MBA can play a role to define and work with those firms like what this model will look like. If I have to give an analogy of this, 15 years ago when cloud was new, a lot of this system integrator and big companies like Deloitte of the world were defining what is the cloud computing model, right? And they built a business around that. If I have to give a golden nugget here to you all, how can a firm be ready for the quantum computing and the risk associated with procuring the technology in this? There's a big issue for every organization. So all this consulting like BCG or Deloitte of the world, they are working to make the firms and even the public sector ready for the quantum. So if you apply for those jobs as an analyst or a consultant, right, after your graduation course, so you guys can create a niche for yourself in this field by saying like, or doing some project or your thesis project or your course project. How can a organization be quantum ready in the next 3 to 5 years? Now this is a very high level I'm saying, but then you have to dissect it. What it means for the CTO, what it means for the CEOs, what it means for the procurement guys. So this whole thing is very new. I don't think there is enough literature out, or there may be, but be part of that. There is an opportunity. You guys can publish some of those as a paper, or if you guys want to even be creative, IP and patents,
Yeah.
Sam, do you mind taking that as well?
The question was about handholding, right?
Or any type of like training program.
We don't have a formal training program. I'll say that our head of quantum business development had no background in quantum computing before he started. You kind of pick it up. I think quantum computing as a field is so nascent that the downside is maybe there's not like a formal training. The upside is that you probably don't need one, and like you don't have that far to go to get to where you can contribute. And there's yeah, I mean, there are lots of great tutorials online, lots of great like resources online. So I would suggest starting with some of those, and I can recommend specific ones. But yeah, I don't know of like formal on-the-job training in quantum because it's so new and not huge at big companies or.
Yeah.
And I'll just add that too, saying, right, on the business side, certainly you don't need handholding, right? You can read some of these intro books to quantum computing, you know, some are heavier on the math, some are lighter on the math, to start getting the basics, kind of understand possibilities. But typically, right, classically the way we work with our clients, we're a SaaS company, but we tend to work through proof of concepts with our clients first, right? Have them start to understand how do you translate the thing you're an expert on, and how do you transfer that to a quantum computer, right? We're working with Rolls-Royce right now, their avionics division, and they're experts at computational fluid dynamics. They know everything about it. They just need help figuring out how do I transfer this computational fluid dynamic calculation to a quantum computer? What does that translation look like? How do I leverage this? And that might need a little bit of assistance getting that first step going through that. So certainly, Classic, our company, does that when we work with you with the software, but there's plenty of companies that'll also assist you with that process.
Yeah, as Sam was saying, there is no formal, right? Means if the closest to the formal is internship, and you apply for internship at this company, including AWS, you can very well say like, I am interested in the quantum HPC, and if you guys have some work done, it will get noticed. Hackathon, be part of the hackathon, it is informal way again. Quantum, one I can think for the business, since you are from the business concentration, Deloitte opened up a quantum weather climate change kind of like a hackathon. It will run for next 5 to 6 months. That is also probably informal way to get together with the like-minded people and then start working on the problem. Now, generally, I have seen over the one which I attended last hackathon from Deloitte was like, there was a technical portion to that. There is a business portion to that. The business portion is you need to define what the problem is, why the problem is needed, for whom, and then, you know, give whole business outline how this will solve. And then the issue there was like how to use the charge from the electric vehicle in a supermarket, and how to use the sun energy in that supermarket with the solar, what will be the business model? So that some of the participants participated purely on the business side, not the technical, they're technical people. And then this whole defining what does it mean to be a quantum ready in the firm, that is a big topic, risk associated with it. The ethics, laws on the quantum side, this also, probably you guys have covered this in your business course, right? The business law and the marketing and all. So think of some novel ways, and then if someone comes to us as a student, because I'm also a student, like they prescribe like do it this way, or they don't answer your question, that means there is no solution, perfect solution out there, and you guys can contribute to that by writing some white paper and defining those business models. That's how I think people will get noticed when you will apply on those internship, on your profile or resume. It's mentioned like you participated in this activity, you created this business model for this particular issue, defining the problem statement, what was the solution, how you solved it. That will probably lead you a job, and I think that will happen in some of these firms, including AWS and some of the system integrators, global system integrators. And then when you are formally in the program as an intern, that is the formal way where you get on the job training, right?
Thank you.
Okay, you want to go to your question list or do we open it to the floor?
Again, I didn't hear it.
Oh, I said, do you want to run through your question list or do we open it to the floor? I do have some questions.
Go ahead, feel free. We have-
Okay, yeah, so I came from a management consulting background. I'm also sponsored, so I am trying to go back after that. I think so my company, unlike McKinsey and BCG, we don't really invest a lot of time and effort in quantum computing. And I was speaking to a partner yesterday and he's like, what's the use case, right? It's so technical. So I want to hear from any of you here, what are some reasons you think that might prevent quantum computing from taking off? I know, Eric, you mentioned a few things like talent, for example. And honestly, I do think I'm a bit skeptical of quantum computing taking off, it being mainstream in the future. And I'm wondering from your perspective, what might prevent that, especially like NVIDIA, when you're investing so much money into R&D, building chips and things like that. How do you know that it will take off, or what might prevent that from taking off in the next 5 years?
Redstone?
Want to take Redstone? It's for blocks.
I'm happy to start. Well, I think will it take off and will it take off in the next 5 years are very different questions. I'm very bullish long term on quantum computing. It's at a fundamental physical level, a different way to compute, utilizing like a much more powerful resources in a way. So there are already known quantum algorithms with proven speedups on useful problems, and I expect more will be discovered, and there will be use cases that we haven't thought of yet. I think the potential for that to happen in the next 5 years is often overstated. Quantum computers are limited in general in what they can do, and very limited right now. So because they're essentially analog computers that rely on protecting a very fragile quantum state while you need to do fast, precise control and many operations, and any error that happens propagates through the whole calculation. It's a large number of extremely hard engineering challenges to get to quantum computers that can do something better than the best classical computers. Now we've already come a really long way at that. Like it's pretty miraculous. And so one reason to be optimistic is we've gotten to systems with tens of qubits where the error rate is less than 1% per operation, and getting from there to thousands of qubits where the error rate is orders of magnitude lower is daunting, but it's not so daunting compared to how far we've already come. So I would say there's lots of reason to be optimistic long term, but the timeline and possibility for that to happen in the next 5 years may be the thing that's overhyped.
Yeah. So it's a good question, and the answer to that will get defined, or it's getting defined as we progress. What will happen next year versus what will happen in 10 years, we don't know. It's not a question about if this will happen. When is the question? When it will happen. And when it happens, if we are not prepared for that change, and if we follow the sequential model, like, okay, hardware has to be ready and it has to support million qubits and all that, and then the firms or the organization who want to play in the software application, they want to wait, and then they want to start, it may be a little late, because they will lose the first mover advantage. And this is very relevant if we dissect the whole industry into the various business use cases. And one of the business use cases I tried explaining yesterday when I said like the whole CPA Act, the Cybersecurity Preparedness Act, it is based on national security implication because your current encryption scheme can be broken. We know that, it's proven. The Shor's algorithm has proven it will be broken. But when? If it gets broken in the next 2 years, are we prepared as a firm, as a government agencies to secure our data of our citizen, or banks are prepared to secure their encryption? What will happen? So all of this will happen. And now whoever moves first will have their first mover's advantage and they can come up with a novel solution. You don't need everything to lay out in terms of million qubits to start your experiment. You can start your experiment today and start at a small scale and you can bet. Since you mentioned your management consulting, all this major consulting, whether it is Deloitte or BCG, and I used to work at Deloitte, so I know how they operate. In the sense, they always see, including the AWS, we see 36 month, the whole landscape, like what will be relevant in this world, in the quantum world, and I think a lot of work is going in the cryptographic side, and there is a lot of push from the government across the globe, including the US government. And if you've seen recent article, I think it was last night, I believe, last night or yesterday, Xanadu, I think not Xanadu, the Pascal, the neutral atom out of France, they got 100 million from a venture capitalist. Mm-hmm. And then there was a Xanadu a few days back, they also acquired. So this is only possible because somebody came up with this whole idea, and there is a concrete evidence from the research scientists and the organization and the government. That is why this is happening. Otherwise, we will not be sitting in this room talking about why quantum. The why quantum is answered. The when is getting decided, and who makes most out of this will be the first mover advantage, including you, including me, and the organization like AWS or anything. It was very philosophical talk, but I hope it's probably clearing some things.
Thank you.
I'll just add to that. My thoughts on what it's going to take for quantum computing to take off, right? A little bit what you talked about, Sam's, right? We need larger and less noisy quantum computers. And right, we talked about the talent shortage, and then I think that'll clear itself up, right? If you build it, they will come, right? People are going to come into the industry. I'm not so worried about that. We're seeing more universities, right, come up with these programs to educate students, and so the talent gap will be filled eventually. What might limit the industry is the scalability of these systems and the noise of these systems, right? We need these two things we need scale up and less noisy qubits to really hit business value. So if one of those two things hits a hiccup, then we're in trouble.
This actually leads to a good question for you, Sam. We now live in this mini scale, right? We have noisy, intermediate scale quantum computers. So they are not big enough and they are noisy. And then NVIDIA comes into play. But NVIDIA is known for graphic cards. So all of a sudden we know CUDA for GPU, and then we get cuQuantum for not a quantum computer, but a quantum virtual machine. Right, so what's the deal with that?
Well said. So NVIDIA does not build a quantum computer ourselves, but for our entire existence, basically have worked on trying to be leaders in accelerated computing, bringing in new technologies, making them faster, making them easier to use, and we see quantum computing fitting into that as accelerated computing of the future. So what NVIDIA is doing now can be divided into first of all, using the tools we have now, accelerated classical computing, to build useful things and useful platforms for quantum computing. So the first thing we did there was in simulation. If you try to use the quantum processors that exist today, not only are they too small and too noisy to have an advantage, it's hard to kind of do research. Like if you're a quantum algorithms researcher trying to develop or test something for computational chemistry, if you can only do a few operations, it's hard to learn anything. And these are important problems that need to get solved. So the combination of those two things mean that simulation has a really important role. And so we're building software and hardware to enable really fast simulation at large scale, to enable quantum algorithms research, quantum computing research, understanding of where and when for a particular problem quantum computers might become useful. And then kind of the flip side of that, the flip side of how classical computing can be useful for quantum is how quantum can be useful and fit into accelerated computing systems. So we expect that quantum computers will be better for some things and just never better for a good number of things. So for example, something that's very easy on a classical computer, like making a copy of data, is just impossible on a quantum computer because of the nature of quantum physics. So what that means is what we think the system will look like is a mix of CPUs and GPUs and QPUs all working together with the researcher or the programmer or the user able to write code that uses each of them to do what they do best. And so NVIDIA has some experience in building such a system and making it useful for CPUs and GPUs. And so now we're working on that to enable QPUs as well.
You mentioned simulation, and it's not just like simulating a molecule or a protein. You have the A100 GPUs sitting in AWS Palm, and you're actually simulating a quantum computer on it, right? So you send a job, you treat it as it was a quantum computer, but it's the GPU that is doing all those matrix multiplication behind the scene, and you simulate the quantum environment, basically, right? So
Yeah. Thanks. That's a good clarification. Exactly. It's simulating a quantum computer, getting the results back that you would get either if you had a perfect quantum computer, but you can also simulate a noisy quantum computer if you want to understand that better. It turns out that a lot of the math needed to do quantum computing or at least simulate quantum computing is similar to what you need to do for AI and large scale AI. And so GPUs are a really nice tool for doing that quickly.
So you kind of see it as a patch that we have for now, or is it something that might stay with us, right? So for example, one might think of, I'll build a small proof of concept or a small scale application. I'll test it out on a simulator. I'll debug everything that I have, and then I can deploy it on a large scale. So which one of these, maybe both?
I think both, and I think it'll be around for quite a while. So certainly for verification and validation of what you're doing before you run on real hardware, it makes sense to do that in simulation. But I think also for fundamental research, for understanding, for this problem, how good will the quantum algorithm be? Can I make changes to it that will improve the scaling behavior or the sensitivity to noise with a well-controlled and powerful simulation environment? That's really kind of where you want to do that. As far as when quantum computers are powerful enough, large enough, available enough that that's less important. I think that's many years away.
And kind of circling back to some of the discussion that happened before about like the transition, like breaking again into this quantum industry, right? You got your PhD from Stanford, you did applied physics, but unrelated to quantum computing. Then you started working with Rigetti, you were a quantum engineer, and with Keysight, your R&D physicist. Then you moved to NVIDIA and you became like a product manager, now you're a team leader. So how was this transition for you? And afterwards, if you can continue, like what are these products that we are talking about, right? So what are the offerings that you have from NVIDIA?
Sure. Yeah, so I did physics in grad school. It was not quantum computing, but there was some, or a lot of technical overlap. So nanofabrication and measurement of systems at low temperature, both of which are useful for superconducting qubits. And I've sort of traversed the whole quantum computing stack at this point. I started out at Rigetti building out their fab facility for quantum chips, and moved from there into the quantum engineering side, and then into the software and software product side slowly. And so I think maybe one thing that's useful to take from that is a startup can be a really good option for breaking in. First of all, because they're probably more willing to take a chance on people without direct experience, but with relevant experience who can bring something. And because once you're there are just a million things that need doing and not enough people to do it. So if you're eager, it's pretty easy to kind of move around and get different experience and take your career in whatever direction you want to take it. And the second part was what products we're building, or have built. So we have a product for simulation it's called cuQuantum. And the way that it works is it kind of fits in underneath some of the frameworks that you've maybe used in this class for defining and running quantum circuits. So Cirq or Qiskit or PennyLane, you can run cuQuantum underneath them and get acceleration on GPUs without having to change your code. It's also available on Amazon Braket. It's also integrated with Classix platform, among others. It's kind of a nice thing because everybody has a use for simulation. Everybody would like it to be faster. Everybody would like to do it at more scale, and so we get to be partners to the whole ecosystem. And the second product we have is called CODA. If you're familiar with anything NVIDIA does, it's very analogous to what CUDA does for GPUs. If you're not, that's fine. What CODA is kind of what I talked about before, a framework to enable developers to program CPUs, GPUs, and QPUs kind of all together in one environment and in a way where you can take advantage of the best tools for classical computing alongside quantum computing. So say you're doing some kind of like hybrid quantum machine learning algorithm, you probably want to use accelerated PyTorch or TensorFlow for the classical side. And so CODA makes that very easy, makes it very easy to access different types of simulators and different types of quantum hardware. We also have an effort towards hardware integration of quantum computing and classical computing, in addition to software integration, but that's kind of to be announced later. So only so much to say right now.
I'll say I'm a big fan of simulators right now, especially in the NISQ era, because simulators don't need to be taken offline to recalibrate their qubits, right? So it's always going to be available. It's always going to be a shorter queue when you're putting in your job. So yeah, love simulators.
And so you all mentioned that you have some kind of partnership with the other organization. Now it really makes sense because you all represent the same technology, so you come from cloud or hardware and another software and hardware kind of thing and a platform. So for you guys to form those partnerships and host each other's technology, it makes a lot of sense, it's really, right? But all of you as well, you have kind of like customer-facing side in your role. And then comes the question, how do you market, how do you sell something which is not quite there yet, right? You want people to start using it, you want people to actually pay for it, a little amount or a large amount, it's a different question, but you want people to pay for something, you're telling them it's not ready yet. How do you do it?
Yeah, no, that's a great question, right? We talked a little bit about this in yesterday's class, right? Preparing for quantum advantage. A lot of companies are building quantum technologies into their digital transformation roadmaps, and they want to make sure they have personnel and staff who understand how to use these systems, that they can take advantage of them, that they understand where the benefit might lie for their company or not. So they need to start investigating it. They have, some companies have skunkworks teams working on this. Some are working with, some of these agencies who will help them and support them in this process and figuring out what class of problems in their business might take advantage of quantum. But also to start investigating, right, the intellectual property of quantum. You need to start playing around with it. You need to start investigating it to see, is this something we can start looking into? Because a lot of companies are interested in that patenting aspect, right? And you need to be able to teach it sufficiently well enough to write the patents, so you actually get it granted. So there's quite a few teams looking into it also from that avenue, right? Patents last 20 years, but all the analysts are saying definitely the advantage is coming well before that, right? Next 5 years, questionable, but certainly within the next 10, we're gonna see some great advantage. And because patents last 20 years, a lot of companies don't wanna be fenced out of their own industry when it comes to quantum. So certainly a lot of companies are coming to Classic. I don't know about AWS or NVIDIA, but they're looking into it for a lot of these reasons, kind of strategy and for determining what's best for their business come quantum advantage.
Yeah, I think intellectual honesty is very important. We try to start with that and make sure that we're not overhyping things when we talk to customers, but focusing on what is actually valuable for you to do today. So one example, Johnson & Johnson is one of our customers in quantum, looking at quantum computing applications for drug discovery. And so what we said there was, okay, let's start with your hard computational problems. First of all, which ones can be tackled by AI, and which ones are we not really going to hit a limit for a while with AI, or just high performance classical computing in general, because quantum computing is, it's an investment. It's a ways away from actual production value. So that's not so worth it. And then of things that are pretty classically intractable, there are some where there's promise for a quantum advantage, and let's focus on those. Let's look at the best candidate algorithms today. Let's start simulating that. Let's start doing estimation of what we're going to need from a quantum computer to see advantage on those problems. What the architecture might look like. It's more than just number of qubits. It's how they're connected, what gates you need. And so really having a good understanding of that now or as soon as possible gives you a competitive advantage once quantum hardware is ready. And it's sort of similar across industries for different problems.
Yeah, please. Just
on follow-up question on that, right? I have the idea of cannibalization. I don't know about NVIDIA as much, but I know, for example, Amazon, they have a SageMaker studio that allows people to do like optimization on that kind of ML platform. And then you have this quantum computing as well. So, and then for NVIDIA, I'm guessing Johnson & Johnson, for example, now using classical computers, at some point, if quantum becomes advanced enough, they might transition to that. So you end up cannibalizing your own customers. I'm wondering if that's a problem that you're thinking about, and if so, how do you manage that?
Mm-hmm. Yeah, it's a really interesting question. So I really don't think so in terms of are we cannibalizing ourselves, because getting quantum computing to work well requires quite a lot of classical computing. So to start, a lot of algorithms are hybrid and require a lot of classical processing. And then even for fault-tolerant quantum computing, where in principle you're submitting something to the quantum computer and it doesn't need too much else. In order to do the the quantum error correction that's required at system scale, that becomes very computationally challenging. And calibrating that system becomes very computationally challenging. And so if you look at kind of what big supercomputing centers are doing, what government initiatives are doing, it's all around how do we tightly integrate quantum computing with classical computing. And so we expect what it will look like even in industry long term is quantum computing kind of fitting in as part of their system.
Yeah, I would certainly say, just because this one hits home, I live in Rochester, New York, right, home of Kodak, and this starts getting into kind of a case study, right? If you're ever worried about cannibalization of your own customers, when you're faced with a new technology, you absolutely have to worry about, right, are you going to cannibalize your own revenue? Are you sacrificing your own clients to move them from one bin to another? Don't shy away from that possibility if it means you're going to be at the forefront of new technologies that are going to take over, right? Kodak they patented the first, digital camera, but Kodak's business was chemicals. It wasn't actually in the film, it was in the development of the film, right? Their whole chemicals business was most of the revenue, so digital cameras would absolutely have cannibalized all of that. Well, you saw what happened when they didn't move forward with digital cameras, they got left behind. And so that's absolutely something, there's definitely pros and cons there, but don't be so worried about that you don't move forward with these new technologies.
I think that one way to look at this problem is the problem is complex, right? And I think there's one individual or one firm can't address this. I think we at AWS realized long back, not only for quantum, but even in the AI side, on the classical side too. So we believe in a partnership with NVIDIA or Classic to co-build this. What we are good at on AWS side is the scalability of the cloud. How you can, and another aspect is the agility of experimentation. So under one roof in the bracket, you get access to the 5 GPUs, different modality, IonQ, Nine-Trapped-1, Photonic. And when as a research scientist or algorithm developer, I write my algorithm, I want to test it, I want to benchmark it. You can do it in the bracket side. But apart from that, why don't we think of like force multiplying with partnership? Like we bring Classic software, which is good at defining a domain model, and then you can get the circuit out. But there are other companies which I talk daily, like Good Chemistry out of Vancouver, GIJ out of Japan. The whole things need a little bit of co-building, co-trusting each other, building that solution together. So everyone has a role, including the chip provider, GPU providers, or the cloud hyperscalers, and the partners like Classic, and there's few of them. And we talked about simulation, as Sam said, like a lot of horsepower is needed. It's just not the quantum, it is the hybrid of the classical CPU, GPUs, pre-processing, and once the quantum spit the output, it is post-processed in the classical world. So you need that hybrid to survive in the near future way of coding the algorithm, right? The opportunities, means quantum computing is one aspect, but then you have a whole of the other quantum technology, the sensing, the communication part. What if suddenly, like, someone comes up with a quantum computer in the next 5 years, few of them lying in their data center, how are they going to talk? You need internet for that, and that is quantum internet, right? So someone has to start in that direction. And doing it alone at AWS, we don't believe in that. We believe we need to have a sound partnership. So that's the reason we announced our partnership with Harvard to work on the quantum internet and quantum networking or communication side of the house. And I think we see the same pattern across the other firms too. They are coming together to solve the problems. And there was a connected question yesterday, like, where is the standard? Standard, even on the classical side, it took some years to develop a standard, whether it was WW or whether a institute like the agency in the government side, the NIST, to define what those standards for the cloud or the classical side would be. On the quantum side, same thing will happen. It's no different. And since you are very familiar with the SageMaker, I probably tried a few of those algorithms. There is a manage instance on the bracket too for the experiment, and you guys can use it to submit a job in the job from the classic computing side and get the output back and experiment with that. So, couple of things I said, right? The partnership and alliance between the hyperscaler, between the chip provider, between some of the ISVs of classic computing, classic companies like, and then the rate of experiment, and then adapting the result of that experiment so that you can have your plan B, plan C is the key, right? So when you as a firm is developing a IP, thinking of developing an IP in that field, you need to take incremental step, right? Whether it is simulation, and I can give an example. This is like traveling salesman problem, very relevant for the logistic and supply chain. You guys might have encountered those in your MBA course, like how to deliver a package for the last mile, how to solve that problem. There are classical algorithms, no doubt about that. But where does quantum fare better? And then that is because of the parallelism, right? Since you can have 2 to the power n and n get big, you can simulate it faster, you can get the result back faster. So that is perfect way to solve the optimization problem. Any work scheduling problem, nurse schedules or doctor schedules at the hospital, or the flight schedule. Right now there are algorithms, but why is that we are saying like some of those optimization problems are suited for the quantum? Because it can run at exponential speed. You take exponential time on the classical side, but you can do it in a polynomial time. Some of that you saw in the coursework, the P space and the BQP space and all that. That is also an advantage to some of the business folks. The engineers would probably come up with some new algorithm, but how are you going to put a flavor of the business angle to that? What problem you are solving with that? So optimization, apart from the simulation, cryptography, everything has a two flavor to that, business and a technical. And for the graduate student who are on the business side, it's a perfect opportunity to come up with those business models. There's an opportunity there. I don't know if I straight from the question, but I gave you like overall very big answer.
I do want to push a little bit on something you said. You all discussed the importance of collaboration and cooperation now and building trust, but AWS is actually doing something they did in 2015. Right? In 2015, AWS acquired Annapurna Labs, a startup from Israel, because up until that point, you were using mostly Intel and AMD chips for the server side. Then you bought them, and now you have your own chips, the Graviton. Earlier in this talk, you mentioned the new center that you built in Pasadena with Caltech. So now you're building your own hardware. So you're kind of cannibalizing, or at least taking a share in this pie from your partners, right? The other vendors that are hosted on AWS, right? So how do you manage this kind of conflict in interest where on one side you want something to be done your way, but you still need to play along with the others, right? How can you balance this problem?
Yeah, the answer to that is like, it's not classical computing versus quantum computing, or it's not like AWS versus the partner, all the other QPUs which are there. So we believe in, we think from the customer angle. Customer obsession is our leadership principle. We, or I as an algorithm developer, should have access to the multiple modalities. Multiple modality means like I should have access to the superconducting based machine or photonic, or even one which we are building is superconducting. Now, when that will get announced or built, no one knows about it, even I don't have that knowledge. It's not about cannibalizing CPU, GPU versus the quantum. In the end, as an algorithm developer, I should have a choice how I want to design my software for example, say for autonomous vehicle, which is in the realm of AI because you need to do a lot of computer vision and all that. So you need the CPU, GPU to do that in intermediate time, which is this NISQ era. But will be able to convert ourselves 100% in next 15 years? I am bullish on that. And that depends upon the access to this hardware to the young folks who will be experimenting with this and other folks who are building this. So if you see, there is already a partnership happening. It's not like we will say you don't have access to the other GPUs or our own CPUs or GPUs too. It's about the choice. And then when you built it, some of the nicest ideas come from the algorithm developer or the research scientist, and they need that choices when they are experimenting in the labs, some of the national labs or some of the R&D department of the organization. We don't want to say like use this versus that. We want to give a platform. That's how I think we play. We give that playing field to everyone, and they make their choices whether they want to run it on CPU, whether they want to run on the GPUs, and or whether they want to run it hybrid, for hybrid machine learning, the VQE and all. Because one thing on the GPU side or the quantum side, like you don't have quantum memory. So when you don't have a quantum memory, the resources which are the quantum qubits are limited. That is your prime thing. You need to think about like how you're going to use that QPUs. So people came up with this nice idea, hybrid VQE. So you do a lot of pre-processing of the setting the parameter and optimizing the parameter on the classical side, but then you just have a call to the quantum and then get the result back, do the post-processing. So there is it depends upon the use cases too, right? Like which use cases we are talking. But at the end, it's not like CPU versus GPUs or our partner versus our own. It's about giving the choices to the masses so that in the long run, if the product is better, it will be mass adopted. So that's the thought process there.
I'm not throwing the fastballs here.
Yeah, so here's another one for all of you. Yesterday we talked about the hype in the media and all this kind of stuff, but once you get into it, it's a very small industry at the moment. There are not many players, not many people working in it, and we kind of see that we are in this honeymoon phase where everybody is very collaborative and everybody wants to work with everybody, but eventually business is business and it will come to an end. And then your partner might be your competition. So from your different perspectives on this business, when do you expect this kind of like maturity to happen? And if you have a prediction of how the market will look like post this breakup, let's call it?
There is again, it depends upon which field we are talking about, right? Like, there is no reason for the White House and Biden to make it a law, which is Cyber Preparedness Act, and it has a definite timeline there. When the agency have to respond for the plan, and then when they will move. There is a seriousness about that because there is a national security implication which anyone faces, like Canada or Europe or China or Japan, right? Everyone are worried about this encryption, and because of that, there is no choice. Means we, as a firm, organization, private sector and public sector, need to come together and solve this problem. That was the very reason the NIST published 4 algorithm, so that before you move to the quantum, we need to protect the classical infrastructure from the quantum attack, right? The famous example of Alice Bob, and there is the third one, Eves, right? We always talk about this eavesdropper who is always trying to break the classical encryption. That's the reason I said, like, you need to pick this into 4 or 5 buckets, right? What it means for simulation versus optimization versus machine learning versus the cryptography. And if I have to predict which one will be faster adopted, I don't think I can say that for sure. But what I know from the venture capitalist and government agency being the biggest venture capitalist, we see the money funded by Australian last year and Canada and now Europe and USA. And there is a reason for that. And this is proven out by the community. So we should take a step back instead of questioning like whether it will become a mainstream, when it will be, or if it will. I think answer to the if is defined, it will. But when, it will get defined when we will have the fault tolerant quantum. But going back to what I was saying earlier, do you want to wait 10 years and then start versus start understanding your business or your IP, and all of those business building an IP or software or the product take years to build, right? You experiment today and then you do the prototyping, development. We are talking about 4 or 5 years of time building a product which is suitable for that particular industry. So either you want to wait up 5 years and then decide, maybe, choice is again about the choices. But what I see from the Gartner or BCG reports, you will see this hype and then it will come down and it will again climb up. That is no different than any other pattern which we have seen on the classical side. It's always the case. It builds up, comes down, and again. The last point on that, if this is just a myth or it's like a fiction, last year's Nobel Prize for the physics would not have been announced and given to those 3 gentlemen who had been doing this work from last 30, 40 years, and that was the individual work, not even together, individual work by these people. We are getting press nowadays more, but work has been going from last 100 plus years. If you go back to the history from the Planck's theory and then the whole EPR paradox, and that EPR paradox was entanglement based on that the groundwork by the Bell and then others, Alan Aspect and all. That's why the physics prize for the quantum was given. So there is a couple of trends if you see from the government side, from the research scientist side. It's not just the fiction. Actually, it is happening. We are in middle of that. And it is an opportunity. I think personally, it is an opportunity for all of you to be in this field. And the very reason why we are meeting today is inspire you all and get inspired back. So all those questions which you guys were asking yesterday are all are relevant questions. And if you feel like 3 of us are not giving you the 100% correct answer, there is a reason for that. It is an active area of research. No one knows for sure this is what is going to happen and when it is going to happen. So all that is, we need to take with a grain of salt, right? And have our own studies and assumptions. But I don't see any reason that we doubt it and then we are late, personal level or as well as the organization level. I think this may be the golden opportunity. And I'm happy, and I transitioned after 22 years in the classical in the quantum. I took that decision, but yeah, fine. If I don't see the actual quantum computer before I retire, fine. But at least I'm part of the chain or part of the system who will try to solve one thing or the other in the due course of next 10 to 15 years. Again, philosophical rant, but it's because I saw some apprehension like when or why quantum and all that, and then people sometimes predict like this is going to happen, but no one knows about for sure. And then understanding what quantum computer can do is a good thing, but we also need to understand what it can't do by when, the timeline. That is important.
Yeah, I think that I'd like to hear what the people getting MBAs and people coming from management consulting have to say about that question. I'm just a physicist, I don't know.
Product manager now.
Yeah. I think a big turning point will be clear value in production, and actual large amounts of revenue from enterprise rather than the case right now, which is often from from government, from venture capital, where, you know, their priorities are more around kind of building a national quantum workforce, you know, becoming leaders in quantum computing, and so the incentives are almost completely to be collaborative. But when there's value in production and it's something that companies really want to pay a lot of money for, then it becomes you know, much stronger incentive to be competitive and much more of a shaking out on hardware, software, and applications. And I really don't know enough to say any more than that.
No, I totally agree with that, right? I think if I have to prognosticate, my PR team has asked me way too often to prognosticate. I'd say right, probably when the first industry vertical hits up probably $1 billion of extractable revenue is when we're gonna see this loss of kumbaya, right? We're all very happy to share information right now, and competition will get much more fierce at that point, but also after that point, we'll probably see a strengthening of the relationships that have been built before that, right? Probably more formal relationships across companies as competition increases.
So you kind of say like camping and like aggregation, like maybe more mergers and acquisition between smaller ones, and kind of like going to maybe 2, 3, 4 leaders in this market that will try to give service to everybody.
I'm not saying so much, right, mergers and acquisitions, right? That might occur, but certainly, right, more formal partnerships between, you know, these kinds of players in the vertical. You might see, you know, vertical chain partnerships occur where, you know, you have a couple of chains that are all these companies are kind of interconnected quite deeply.
So you think like a vendor will specialize in a type of vertical and then they will service this community and
Yeah, and you might see, you know, exclusivity of a certain, you know, maybe a software vendor exclusively works with a particular hardware vendor and things like that.
And some of that is started happening informally out of Europe. BMW, BASF, Boeing, and few others I'm forgetting. They have formed this informal kind of like collaboration between them, and based on the material science and then the drug discovery and chemical decomposition of the molecule and all, which is a common problem. If you see like BASF, the BMW electric vehicle, right, and then the Boeing, Airbus and all. So they are coming together because everyone needs like new way to design a material, a new molecule to be found, right? It's a common problem. On the drug discovery side, like it takes years and years to simulate a molecule and understand what factors, how energy affect and all that, so they can come up with the effective drug. So that is why we don't see other drug discovery, or we don't see new drugs like every 6 months or every 3 months. It takes like probably 10 years between launching and trial and all that, but a lot of time in discovering those molecule composition, how they act together with the foreign object and all that. So again, if it is a cryptography, I was saying the government agencies, and we have a big cryptography team in AWS too, which is a separate entity in its own because it focuses a lot on the security aspect of that. And there is a reason why hyperscaler has to think differently, because we house all the major Fortune 500, and you think about like how to make it secure and all. Not only on the classical side, but thinking ahead, like okay, someone will probably is working in a garage trying to break the classical encryption, and he is not going to announce and come and say like I'm going to do on this day, right? We need to be prepping up before that happens, and so again, it depends upon which vertical or which use cases you are thinking, whether it is simulation, whether it is optimization, right? And sometimes it is the business value, direct business value. You can see it from a business leader standpoint. What is my value out of this, doing this? Sometimes you don't have an option because it is a national security implication. You have to prepare for the worst, right? And then not to be like everyone's credit card are decrypted and bitcoins are gone from their account. So organization have to think ahead, like 36 months, 10 years, what can happen and prepare for that. And you can't wait for that to happen in sequential order. So you need to think about like how you can prepare now to act later.
I'm actually just gonna grab my phone so I don't miss the catering order.
Maybe on kind of like a more positive note. You said I hope you were joking, but we hope to see it within your lifetime. That we have fault-tolerant quantum computer, fully scale, fully usable. For each one of you, let's assume you wake up tomorrow morning and we have everything working. Everything is working. What would be this one problem you would like to see solved? What is one thing that really bothers you that you really want to solve using quantum computer?
What about first?
Personal wish.
Personal? Ooh,
Yeah.
okay.
It's 11:11, so your wish will come true.
Better
Say it quick.
better say it in the next minute. Yeah, I mean, I'm not a biologist and don't know much about drug discovery, but that to me seems like the biggest confluence of reasonably possible with a quantum computer. People throw out solutions for everything, but there's a reasonable path for that, and huge impact on society. So being able to do, very large scale simulation of chemical reactions, simulation of biological reactions, has huge impact for being able to discover new drugs faster, cure diseases faster, and is closely related to much more efficient energy processes. So I don't know if I can like nail a particular disease, but things in that family I think are the most exciting among the reasonably possible.
Certainly, I agree with that, right, Pat, to pick one, it would definitely be that kind of molecular simulation, right, because there's absolutely huge benefits in drug discovery, right, that's gonna save people's lives, right, no doubt. But there's also, tremendous applications for that for materials development, right, we can have cheaper materials, higher strength ratio materials. We can see a lot of benefit globally from that as well, right, having these kind of more easily to produce materials, maybe even local materials out of local materials, right, we can more easily design and develop these things.
Yeah. So I was joking, like whether I will see the quantum computer before I retire, but there was a similar question by someone yesterday. Will I see a quantum computer beside my desk? Now, it may not happen like you have a quantum computer in your computer or in near term, but the question should be, or the right question should be, what as a researcher I have access to today so that I can develop this drug discovery or simulation software. And I think central to all of this would be the ease of access. So you go to probably cloud and then have a multiple modality available to you so that you can design your algorithm if you are a researcher. And then I see that no difference than having an access to quantum computer. Because your use case is I want to access that and then I want to produce something, some novel solution which is not solvable or not tractable in the classical side. And then reason for that is that, right? That's why you want to. It's not like I want to play some music on my quantum computer, right? So you're thinking to solve something which is not going to get solved on the classical side. And hype is good. The work has been going from 100+ years, right? Starting from Bell and Einstein and all that, and Max Planck and all. We are getting press lately because there is a good effort by the public and private sector in defining how the future will look like. That is why you sometimes will see, 10 years, 15 years, but now 5 years. So even though it is shrinking. The timeline, if you see the 5 years ago or 7 years ago report, they will say like, 15 years, we'll see a fault tolerant quantum computer which can produce a production grade application or support that kind of a thing. If you see article from this year or late last year, it has shrunk. And there is a reason for that shrinking, because there is a good work on the error mitigation and all that, and to control the noise and decoherence of the system and all that. Nice algorithms are coming up. So, hype is biggest worry for me sometimes, because the promises should be made and checked by the research scientists. And one of the name comes, and one of the incident happened last year was like this scientists discovering the wormhole and black hole and all that, right? And then immediately scientists like Scott Aronson and all have to issue some clarification to New York Times, which sometimes goes against this whole idea of inspiring you all, but then you hear that back and forth announcement and then redacted and all that, right? So which is not generally good for overall for this community. Because confusion is not good. Ambiguity is sometimes good, but creating this kind of confusion will go against that. So overhyping, overpromising, we need to be really careful. So that's what I think I worry, because I deal with some of our customers and some of the partners, right? How to play this balancing act. So that is the key. Always there will be scope for the HPC and quantum, and in between quantum inspired. You guys will hear the word quantum inspired. So even the organization are staying or playing safe by saying quantum inspired. It's like in between state of this solution. It may start with quantum, very well. HPC cluster or parallel cluster, 1 million cores or GPUs, CPUs are getting spinned up to solve drug discovery or even the autonomous vehicle algorithm designing and then training and all that. It's fair to say like, classical algorithm, every time a new algorithm gets published in the quantum, equally great work is shown by the classical computer scientists. They come up with that path. Because we don't have the qubit yet to prove the full quantum advantage, it is just the information theory, it's based on that complexity theory and all, on the theory side. But as the qubit in size increases, we bring down the noise, you will see those advantages in terms of solutions getting out. And that is the reason people are simulating this. And when the qubit comes on a physical side, they will be ready. So, again, a long answer. Main point is the overhyping. We need to be very careful with overhyping.
I just wanted to disagree with what you said.
Which one?
Regarding like the wormholes and the scientific community disagreeing, I think it's actually good that we're coming back to these things. I mean, you could say that sure the press is like overhyping it and everything, but it's good that we're like readjusting our expectations because it's a very rapidly changing field. So at the same time, like science isn't always about proving you're right, it's also about proving you're wrong. And so it's like always changing. You have to like, reset your expectations, reset your calculations, even, and even proving that you're wrong may be a big improvement for proving that you're right in the future. So I think that it's good that these discussions are happening and yeah, that's it.
Yeah. So, that is the reason I said like Scott Aronson, who is the legend in this field, right? He needed to give some of the, and that is in their website too, if you see in his website, he make a point. And the whole point he was making was like we need to be careful with this over-promising, over-hyping some things.
Yeah.
There was one more thing happened. I think you guys probably know about it. There is this Shor version of the algorithm which we saw, which proves that the RSA encryption will be broken down. Quantum computers will break that. So there was an article, or there was a release last year. there is a very similar name like Schroeder or someone from the China team. They said like they have broken the encryption. Then again, the explanation from the quantum research community happened like it's not the Peter Shor version of the RSA encryption, it's something else. So there is a balancing act. Also, we as an industry leader, you guys will go and run some of the biggest firms in the near future, right? So know the limit to. At the same time, what is possible is getting defined. It's getting defined, and you guys will also define that when someone will propose you like this logistic problem can be solved by 10% in terms of delivery of the package. Those use cases or drug discovery use cases will be valued by the customer in terms of like how much you are saving in terms of cost, and then value engineering side of the house, right? And if someone says like we all have to define after 10 years, I think that is wrong way to look. We need to define some of those outcomes now, right? If I use some of this platform to design my drug, what does it mean? Right now, it may not mean much. It is probably on a theory side of the house, but what you are doing unknowingly is you are prepping for 5 to 10 years ahead of the time. When it happens, you can have a quick switch off the platform of the drug discovery into the quantum side. That is why I get sometimes this whole, some of my partners ask like they want to build a drug discovery onto the cloud. How we do this? Because they are thinking ahead. They want the infrastructure to do this. It's not like fiction. It's not like they suddenly got up and said like, yeah, I want to do this, right? There is a thought process behind this. Yeah.
So you mentioned the field of autonomous machines. What are the current extent and potential future applications of quantum computation in that sector?
Yeah, so if you know Volkswagen, right, and forgetting the university name in Portugal and even the agency name. So I think they came up with this novel idea of routing of the vehicle intelligently. Very relevant use cases in terms of the autonomous vehicle side of the house. Most of the time it is based on the computer vision and all that, GPUs and all that, but what they were trying to solve in that use case was like, how can they use this quantum computing, parallel processing to do the power and scheme of the things to intelligently route the vehicle in short amount of time. And this whole premise is based on, not on the quantum algorithm, but the idea has been around forever, the traveling salesman problem. So they adapted that, they came up with this idea, and they, in the end, they published those results, and then they said like, this can save so much traffic congestion in the cities and all that. So that was the closest thing I saw, something was done in this area. There was another, and I can send you a link after, I'm forgetting, on the unmanned aerial vehicle, there is a, I think it was D-Wave and some of the others who did this whole project, how to control your unmanned vehicle, drones and all, the route so that it doesn't collide with itself, right? So route planning is the center of that. It is again based on the same thing, like how to, model your qubits and all, how to design your best route and all.
Actually, I think in NVIDIA you have like a really nice use case for it. You kind of maybe unrelated for quantum at the moment, but you have Omniverse, like your own version for the multiverse. And you have Isaac, who's supposed to be like a library for machine learning, databases and algorithms and stuff. And I saw a really nice example where, I don't remember if it was BMW or Volkswagen, they created the entire facility within this multiverse, BMW, and then they let the little robots need to go around, train themselves on a virtual world, rather than like in real life. So,
Yeah, I think autonomous driving, we're only just now starting to see, the power of AI for that. So that has quite a bit of runway. And as far as the possibility of quantum computing to contribute, one challenge is like for inference, for like having something on board, it's not so compatible with a lot of like what you need to operate a quantum computer. Also, in general, coming up with answers, processing things very, very fast, in the absolute sense, is tough. Where we see quantum computers being the most useful is when a classical computer like just can't do it. And where that probably hits autonomous driving is, I think, general training in AI, where I'm not going to say there's concrete proof, but there's evidence that for certain types of data, a quantum machine learning model can be more expressive. But if I had to predict, I don't think that will be one of the first areas where it lands.
Yeah, I'm still forgetting one article. It was around the similar line, like how quantum computer will need less data for training and testing in comparison to the classical computer. So that may be a big advantage for the AI, right? Like most of the time you are in this spin cycle of simulation, resimulation, simulation, resimulation, and then testing it out. That is a time consuming. And that is time consuming process, but even in the real world, when you are deploying the algorithm in the vehicle, you need to make those split-second decisions too, based on the algorithm's output, which was trained in the lab. How is that vehicle going to decide the minimum shortest distance to reach from point A to point B? That has to be done real time, on the fly. It's not like you can train everything in the lab, right? That can happen, but various parameters, weather, road condition, other things can affect the autonomous driving at that second, right? So that has split-second decision making. That should be the future, forward-looking, how the autonomous vehicle should behave, right? Not like giving me right now how you see, like, I still get like they do the route planning, but I don't get the precise. It may say like you may save 5 minutes, and by the time I'm on that road, I don't save 5 minutes, I spend 10 minutes more because already people are on that road, right? So it's late, it's a little late. So it's thinking about like millisecond, nanosecond and all, those decision making may not happen in the real time with the classical. If it happens, you need to have a big infrastructure to support that. And then that cost and resource equation goes against the classical side. That is where I think quantum computers, parallel processing, which is 2 to the power n goes larger, you get that whole exponential speed up will come into play.
I have a question for Sam in terms of like chip manufacturing. So I think something that hasn't been brought up is like nuclear politics around the whole chip manufacturing. I know you said in your introduction that you actually laid out the roadmap, right, for the whole like quantum computing build up in terms of hardware. And I'm wondering, how are you ensuring that you can hit your milestones on time, given how much uncertainty there is around like production facilities, as well as the talent movement around countries that are very good at quantum computing?
Are you talking about for quantum computing in particular, or for
Just like chips in general.
NVIDIA's chips?
Yeah.
I mean, for our
quantum computing will be even harder, right? Because I mean the talent's even more niche, and then the technology is even more niche as well. So how do you navigate that? How do you ensure that you are still delivering on time?
Yeah, I mean, so for quantum computing, first, I wouldn't say that it's necessarily harder because the scales are so much smaller and the timelines are more flexible. So right now, for example, a lot of quantum computing, even startups and certainly big companies are doing all their own fab in-house. So building their own facilities, and so there the supply chain doesn't have as much of a direct effect. That will change as things scale, and already you see like some quantum computing startups starting.
As a question regarding the financial side. Like, I know, like R&D is a big chunk of the business and also a big investment from your end customers to even explore quantum computing. Is helping them to understand their ROI and the hurdle to get them involved? Yes or no? So we've seen like there's like free credits there if you try, or you promise them a big potential. If we solve this, then you can achieve something big. Like how do you have any like what's best? What works best for you so far? Just to explain the pricing of your existing products or service, just to get them engaged.
To explain the pricing.
Yeah, like you commit to this pricing. How long the project's going to be? And how can we help you to achieve your goals to make it financially viable for you?
Great question. Depends a lot on who the customer is. One thing that's nice about what we do is, a lot of the value proposition is speed up. So do what you were already doing, but much faster. And so you can show things like, okay, you're already researching these quantum algorithms on an AWS CPU cluster. If you used our software and paid for the GPUs, it would be more expensive per hour, but you'd do the same things so much faster that you'd actually save a lot of money. In addition to getting more power and being able to scale. It really just depends a lot on who the customer is. Like for a lot of our industrial customers, they're also using AI heavily. And so something we can say is, you can kind of get both in the same system. Like right now, you want to already use classical accelerated computing in production, start bringing AI into what you're doing. And what you need right now from quantum is kind of research and development, and you can do that on the same hardware. So you don't have to go spend millions of dollars on just quantum computing. You can buy a system that does everything for you and can be shared. So when you started asking the question, I thought you were asking about how targeting quantum computing for finance. Did I answer your question, or was
Yeah.
Okay?
There are some organizations who are the partners who I work with. They're trying to solve some of the optimization for the portfolio selection. Okay, so they want to build solution around that, and the other ones are like the whole risk analysis on the macroeconomic condition which are happening all over the globe, solution around that. So there are partner, one I can think of like Multiverse out of Spain. They have a solution called a Singularity platform. So the whole idea of why they built that platform was to address that use case. Now, how much of that is a value to the end customer? I think right now, that's not the point. The point is like, can you simulate a system and this whole risk portfolio optimization use case in a quantum side more than a toy problem, like an actual working thing, and show that to the end customer. So that was their goal. Now, how that will progress next in terms of whether the solution would be classical or the hybrid, and I think it may be hybrid, like using Wiki and all that. But check out the solution, Singularity. It's called Multiverse, is the company name, Singularity. It addresses some of those financial use cases. And let me give a different take to what you asked. And I alluded to that yesterday or probably today. That is an opportunity for the business graduate like you to develop a business model around that. As research scientists and companies are coming with the algorithm, the value engineering of that use case, some of that is out in terms of literature by Gartner and then Deloitte of the world. But I see there is a gap, and that is an opportunity where you guys can pitch in and help on particular use, all of these use cases, whether it's finance, the drug simulation, or create a layer above the technology and come up with those modality in terms of like explaining the value engineering of a particular use case to the end customer. That itself is a research to me, where there is a role for being a graduate like you, because some of you will go and work for this management consulting, BCG or Bain or Deloitte or PwC, and their primary job is advising, whether it is AI or cloud or quantum. But then at the end of the day, they always come up with this value-based engineering, because engineering will happen, but they put this flavor of value-based engineering in terms of like how much this will save you, Mr. Customer, by end of this experiment if it goes live, right? So that is an opportunity. What you just asked is an opportunity to come up with some of those white papers or blogs or publication.
Any more questions? Yeah, go ahead.
What might it take to decrease the production cost of quantum computers to make them more accessible to businesses?
Oh, sorry, missed that question.
What might it take to lower the production cost of quantum computers to make them more accessible to businesses and individual consumers, perhaps?
Production cost of quantum hardware so that businesses can use it?
I think maybe I'll try to answer it.
Yeah.
Before I joined Sloan, I worked at Intel for over 6 years. So the thing about some of these technologies, like if we look at superconducting qubits or for silicon quantum dots and this kind of stuff, this is technology we already have, right? It's just a matter of finding the right process, the recipe, as we call it at Intel, and then you just have it. On the other side, you have new technology like photonics, ion trap, neutral atoms. There, you had to kind of borrow technologies from different environments and kind of combine them in this new way to form a quantum computer. Now, R&D part is slow and it's very capital intensive. We're talking like, can reach like hundreds of millions or billions of dollars just to get the process done. But once you know how to do it, scaling up then, this is the easy part, right? Once you need to know that, once you know that you deliver 2, 3, 5 chips a year, this is one way of handling the business, but once you go production and you need to manufacture 1,000 a year or 10,000 a year, then you also enjoy from economies of scale. Then you buy the materials, it actually costs less. So the way we saw it, like at Intel, was we started new technology, like you want to move from 40 nanometers to 10 nanometers to 7 nanometers. You develop everything from scratch. It takes a lot of time, a lot of effort, but once you hit this level of production and you can scale up, then it will probably move much, much faster and cost will go down. In return, you kind of maybe drop the cost of using it because it doesn't cost that much, just to pay for your expenses, right? So, and maybe then it will be more accessible, cost will go down, both to use it and manufacture it. Maybe some companies or departments of the government or national labs, they will buy their own stuff. And so,
Yeah, we're still in a very early phase where if you buy a quantum computer now, you're paying for the dozens of PhDs who worked for years to try a bunch of different materials and run things 1,000 times until they figured out how to get it to work, as well as build up the whole fab. So I agree with Almog. I guess as things evolve and scale, it's kind of naturally going to go down quite a bit.
Go for it.
Quick follow-up question. So TSMC right now has the like 9nm and 7nm chips. So what's the, like, what goes on in deciding whether they should get it from a different company as opposed to build it in-house?
For a quantum computer?
Yeah.
So it depends on the type of quantum computer. So for superconducting qubits, for example, which is what Amazon and IBM and Google and a lot of quantum startups build, it doesn't quite leverage like a very small lithography process in that way. Like each superconducting qubits are scaled microns, and depend on this kind of technology called Josephson junctions that TSMC doesn't really do. So for those groups, it usually makes sense to do things in-house, just because it's not so in line with that. Now for photonics, which is a different way to have qubits and build quantum computers, the processes there do kind of align more closely. So the kind of leading photonics companies are starting to use TSMC or Global Foundries for fabrication. I think it's still not obvious that you want to do that, because that gives you a cycle time that you don't control. It might be 4 months per iteration or 6 months per iteration, and of course they're very busy. Whereas if you have a fab in-house, you can push that and get that way down. And so it kind of depends on what phase of fabrication maturity you're in. If you need to be changing things very fast, maybe it doesn't make sense to go to TSMC. Once you're kind of very confident in architecture and it's about having it produced very reliably by professionals, then maybe the investment is worth it.
Yeah. So what kind of role do you see data connectivity speeds playing in the adoption of, or not adoption, but in quantum computing becoming more widely accepted? Because a lot of examples that you mentioned, especially with regards to mobility, have instances where the data is being collected from the ground, which does not have wide connectivity, right? And there's a limit to how much, how quickly that can come in. And quite a few applications that you mentioned in terms of streamlining, let's say route mapping, traffic advisory or city planning, traffic planning. If it happens with a lag, then it's not that reliable or doable. So how do you think, we've got 5G and all coming, but what do you think will be needed for quantum computing to really become mainstream?
There's a huge role to play for data connectivity. Actually, what you're talking about, which is data collection in the first place, there's a role for something we haven't talked about yet, which is called quantum sensing. And so a lot of the candidates for advantage with quantum machine learning depend on very high quality quantum sensors. And the reason for that is because there's a huge overhead to pay, not just for collecting the data, but for kind of qubitizing it, translating it into something that can be run on a quantum computer. And so quantum sensing with high data rate to a quantum computer is going to be essential for, even if you have a quantum computer powerful enough to do something with an advantage, not getting killed by the overhead of just getting the data in. And then the second part is, for everything that requires things to go back and forth between the quantum computer and the classical computer, right now you're usually limited by having to send that data over the internet because they're not co-located. And we expect what it will eventually move to is a very tightly coupled system, kind of the way systems with GPUs and CPUs work together now, where the focus is on very, very low latency coupling between the quantum computer and whatever classical resources. So yeah, very important, comes in a couple areas.
Because this also brings me something to what you mentioned earlier. You mentioned something along the lines of making a bet for the future, right? It does not happen in a short period of time. So you kind of now this will also kind of translate into what kind of, for lack of a better word, what kind of operating systems, so to say, become more widely adopted. So when you're developing, when each company or each developer is developing their own solutions for it, be it quantum sensors or the computing capabilities, how do you guys predict what will become the underlying operating system, so to say? How do you hedge for that
So,
bet?
Sam mentioned about the sensing part. Going back to where you started, like the mobility planning for the vehicle and all that. And I mentioned earlier this whole internet, that is a quantum internet, the quantum communication one. An easy thing is, like, I would suggest to read one paper. It's about how you can distribute some of the quantum keys for the encryption using a satellite. And this was a research done by some of the Chinese researcher at the European lab. And they distributed the keys with the satellite from 2 ground stations. And then part of that was classic in terms of, like, the local office is connected to the lab using the traditional classical communication, but from that to the satellite and satellite back to another ground station, it was quantum channel which they used, satellite. So problem to solve that mobility is not one technology like a quantum computer availability, but also like the mode of communication. And then there is another problem right now, the way the technology stand is, you cannot have an effective rate of qubit transferring from one point to a long distance with perfect 100% accuracy delivered on the other side, right? So you need some repeaters in between to make that happen. And then whether it's a ground station repeater or whether it's a satellite, we can talk about that. But transferring a signal from point A to 1,000 kilometers, 10,000 kilometers is a big challenge. So some of this infrastructure on the quantum side, the layout of the quantum internet, what does mean, will solidify some of the industry use cases, which is smart mobility. But guess what? Like, if you remove the quantum from the equation and still live in the classical world, so solving the split, the vehicle taking split-second decision to find the most optimum route, where do you keep that algorithm? In the car or in the telecoms, the towers or the satellite? They are getting defined at the moment. And then the role of the low orbit satellite or the role of the telecom providers through their towers are solving that issue, right? Because it's one thing to train the model, but then after the training the model in the car taking that decision has to be in the car or very close to that, so that this can be done in a millisecond or microsecond. So that problem is same when you do it on quantum side too. But apart from the computers, connection of the computer using the internet, using the new way to sense the signals based on that whole radar and metrology, the sensing part, everything plays a role.
So I'll say our good friend Sam needs to be leaving, so.
Yeah, I was just about to say,
Yeah.
unfortunately, I gotta take off.
Sure. Thank you very much, Sam, for being with us.
Thank you, thank you.
Thank you everybody for coming
Yes.
and participating. And
Sam, if you want to take a Chipotle burrito with you, feel free. The last question can be, what are we having for lunch? The answer is Chipotle. Absolutely.
Yeah. If there are, if anybody wants to talk more
Yeah.
or ask questions, feel free to connect on LinkedIn or Eric and Elmog both have my contact info. So, yeah,
Absolutely.
Great meeting you all.
Absolutely.
Thank you, Dan.
All right, thank you all for coming. Okay. Perfect.
Yes.
We can just take a quick selfie with the 3 panelists here, that'd be much appreciated. Let's see here. Unlog. Could you take a photo real quick? Just for all the good fun
We
PR.
want the double cost too afterwards.
Yeah, do it around there, okay. Perfect.
Call and adjustment.
You're taking a photo.
I think that's it.
financial scientific.
This one?
I studied some shit.
What's your question?
I'm not impressed, yeah.
Always good. What makes it work.
Yeah, squeeze it.
Now to the front. You always get.
Welcome to the front.
Alright.
Okay, I'm good.
All in favor?
You have to be in the middle.
Yeah, I don't know how wide you need to go on.
I want you to be in the picture and then.
Okay, let's do a story.
Oh, yeah.
Yeah, go down there.
Alright,
Are you ready?
yeah?
Another one. Just a second. I think this is enough.
Perfect, thank you.
Thank
Perfect.
you.
Alright. Absolutely, alright, well, thank you very much.